Hey dear students, today I am going to discuss about snack-like robot. A snack robot is biologically inspired robot which resembles a biological snack. Snack robot come in many shapes and sizes. All the snack robot have properties that their small cross-section to length ratio allows them to move and maneuver through tight spaces. Their ability to change the shape of their body allow them to perform a wide range of behaviors. Their application extends in many fields. They can be used in medical fields, surveillance system, access and monitor areas which are inaccessible to humans. Over the year, a lot of research has been carried out in its design and control. And in the present world, we have highly sophisticated snack bots which are capable of climbing trees, trunks, swim, and perform highly complex motion. Surveillance is a vital task for defense forces. To know the movement and status of enemy, the national defense uses several equipments including aerial and ground unmanned robot to perform the surveillances and also to attack the enemy. The main drawback of aerial devices is that they can be easily detected and destroyed by the enemy. Similar kind of threat exists for the wheeled unmanned ground vehicles due to their elevation above the ground. Furthermore, several problems are observed while moving in a non-uniform terrain. In such scenario, crawling motion which does not require significant height from the ground is an excellent alternative. Therefore, the trend now is to build autonomous ground vehicles such as snack-like robots that can move on relatively rough terrains and narrow passes. The snack-like robot is provided with a global positioning system and a set of cameras to identify its location for tracking and navigation. The front rotatable camera can be used to have the extended view of target location. The rear camera is used to analyze the motion of robot and to detect the motion of the enemy. Suitable image processing algorithms are required to be developed to process the image captured from the cameras in order to correctly interpret the information collected from the cameras. The robot is also provided with an ultrasonic sensors to detect the obstacles and hence to estimate the required motion pattern to avoid the obstacles. In this context, relevant control algorithms are also need to be developed to retrieve the execute the suitable motion pattern to smoothly avoid the obstacles. With the GPS onboard cameras coupled with proper image processing algorithm, ultrasonic sensors and appropriate control algorithms, the snack-like robot can fulfill the task of surveillance and collect the information related to the enemy military base. Now we discuss snack robot's motion gear generation method to navigate various terrain conditions. A snack-like robot with several motors connected in series is developed to perform the task of surveillance. To move on different terrain conditions, the snack-like robot has to execute various types of motion patterns such as serpentine movement, rectilinear movement, concertina movement, and sight-winding movement. Out of the four cases, most of the snacks are following serpentine motion due to its high efficiency. Rectilinear movement is followed on the smooth surfaces and concertina movement is followed while navigating narrow passes. The creeping locomotion of the snack-like robot is generated by swinging the joints from side to side to cause the forward propelling force which comes from the interactive of the joints with environment through friction. It is important to note that the motion analysis of snake-like robot is carried out by performing the kinematics and dynamic analysis. The assignment of frame for the proposed snake-like robot for finding the forward kinematic solution is given in figure. The kinematic equations of the snake-like robot is established by assigning the coordinate frames at different joints after following the DH parameter notations. Once the coordinate frame are established, the displacement, velocity and acceleration of every link of the snake-like robot are determined through the kinematic equation. The displacement, velocity and acceleration of the link are given by equation 1, 2, 3 respectively, where Li represents the length of the link, Lgi indicate the distance from the gravity center of link I to joint I. Further, theta shows the angle between the direction of link and x-axis of the base coordinate frame. Moreover, pi dot, pi double dot indicate the displacement, velocity and acceleration of link I, and pgi, pg dot I, pg double dot I represents the displacement, velocity and acceleration of the gravity center of link I. Now, if we talk about dynamics of snake-like robot, the angular velocity, angular acceleration and the torque at various joints of the snake-like robot can be estimated using Lagrange-Euler formulation. The generalized force tau at various joints are estimated, where Q double dot represent the generalized displacement, velocity and acceleration of the joint I respectively, and Gi denotes the gravity terms. The mass moment of inertia matrix can be estimated as Mij, and the centrifugal Coriolis force are given by Hij(k), where Ip denote the polar moment of inertia. The acceleration of the link play an important role in controlling the individual joints of the snake-like robot. The expression for the generalized acceleration of link J is given by Qi double dot, where Ijk is equals to 1, 2, 3, so on n. The actual torque required at the joint-based PID controller is given as tau actual is equals to Kp E plus Kd E dot plus Ki integral E dt, where Ki, Kd and Kp represent the integral, derivative and proportional gain for the controllers. Therefore, the error E can be estimated as the difference of final theta if and initial theta is angular displacements of the joint I. The actual torque tau I actual delivered by the controller to each joint is given as tau I actual, that is equals to Kpi theta if minus theta is minus Kd I theta is dot plus Ki I integral E theta is dt, where I is equals to 1, 2, 3, so on till n. The integral terms represent the state variables, namely xi dot has the representation of the state variable is given by xi is equals to integral E theta is dt, xi dot is equals to theta if minus theta is. The generalized acceleration controlling the motion of snake-like robot are derived, that is Qi double dot.
This equation Qi double dot is used to derive the value of proportional, integral and derivative gain of PID controller that satisfies the acceleration requirements of various joints. Furthermore, snack-like robot can be mounted with ultrasonic sensor. The information collected from this sensor is used to detect the obstacles ahead and to decide the type of motion to be executed the snack-like robot.
Hey students, now come to fabrication part of snack-like robot. The snack robot is made of many rotated links. Each link consists of two servo motors. They are fixed in such a way that one motor rotates the link vertically while the other rotates in sideway. The entire snack robot is made up of 7 such links connected to each other. Thus, 14 motors in total. The component used here: servo motors RKI 1206, microcontroller board Arduino Uno, servo driver module SEAL 16 channel. The wires are plugged to the respective terminals of the servo controller board. Power as a whole is supplied to the input terminals of servo controller board. The motors are connected in parallel so that same voltage is provided to each motor. A servo motor requires low input voltage, about 5 to 6 volt, but very high current. Therefore, it is always safe to use a LiPo battery as it can provide a high current input. For the robot motion, various gate, different codes has been written on the Arduino IDE. Those codes for the various motion of robots. For the wireless communication, Zigbee module also used. Zigbee pros S2B and Zigbee adapter is connected through the Arduino IDE and computer, and a wireless communication has been formed to control the robot motion.